Okay, want to have a quick look at phi, the golden mean, the golden ratio, the divine proportion, amongst other names. And it's firstly we'll begin how to find pi, and as always the Vesica is a awesome place to start. So it's basically same thing as always, two circles. Second circle on the edge of the first. And now we'll use a straight edge to cut the Vesica down the middle. So basically from that point to that point. And actually I missed a step, but you can still find the centres of the circles. So let's see the holes in the paper. And we're going to draw a line across. I'll extend this line out a little bit just in case I need it. Okay, so first to begin we have square root of 3. We're going to so we know that that's the radius of the circle, and that's the same distance here. And since we've cut it in half, therefore we can say that this is 1 and that this is 2. So this line here is twice as long as that one because it's the same length there. Cut it in half, therefore it's 1. And therefore we can also say that this is a square root of 3 from Pythagorean theorem, a squared plus b squared equals c squared. So 1 squared, which is 1, plus 4 squared, plus 2 squared, which is 4. Therefore this length is the square root of 3. So a squared 1, so 1 squared or 1, and so that would be x for the moment, equals c squared or 4, and well therefore 1 plus 3 equals 4, and blah blah blah. This is the square root of 3. Now let's open the calculator. So one way to calculate phi, or the golden number, the divine proportion, is 5 plus 1 over 2. And just to have a where are we? Calculator. And we need, there we go. So square root of 5 equals plus 1 equals divided by 2, pardon me, divided by 2 again, so we go back to the original number, divided by 2, 1.61803, so 1.61803398887. It's just like pi, it goes on for infinity and never repeats, and that's the important part, is to remember it's just like phi, so it's one of a transcendental number. Now, so I shouldn't have done that anyway, so I shouldn't have written it there, but so I'm going to, so we still know that this distance by definition is 2. So if I put my, and I'm going to draw just a little bit of an arc there, so therefore this distance is 2, this distance remains 1, and the diagonal now would be the square root of 5. Again, we just a simple way to prove that is in the Pythagorean theorem, a squared plus, so this is the square root of 5, using some of the old-fashioned maths, compass and straight edge. In ancient times this was basically how they did all their proofs, all their maths. So We've opened the compass now to the square root of 5. So it's square root of 5 plus 1. And easy way to, now we're just going to, so this is 1 plus the square root of 5 and divide by 2. We can just bisect the line, put your compass over halfway, draw an arc, draw another arc, and so we've cut this line in half. Now we know that this distance, or that distance, is 1.61803339 ... So from the vesica, it's very easy Pythagorean theorem to prove and to create phi ruler. Now, where are we off to next? Okay, so some other really cool things about phi is it's a beautiful number, a lovely number, and unlike out of all the infinite sea of numbers, it is special in many ways. So what I mean by that, am I still in shot? But geez, I hope I've got all of that in camera. Yep. Okay, so firstly, what is phi? It's one of the symbols for it, or another one, equals phi, the golden ratio, divine proportion. But the number itself, 1.61803398887, and then it's 498 and on to infinity. But why is this number so special? Many reasons. In nature, pine cone, sunflowers, shells all encode this same lovely number, and the pentagram is geometrically beautiful in regards to this number as well. But strictly speaking, so what's really cool about that is, and unlike any other number in nature, this only works with phi. The golden ratio, the divine proportion, only with this particular number. And so, for instance, phi plus 1, or 2.618, equals phi squared. Phi minus 1 equals 1 divided by phi. So again, only this number will it work, but phi sort of seems to be a number that's hiding underneath all other numbers. You might even, might even say all numbers are built on phi, and what do I mean by that? So for instance, 1 equals phi minus 1 over phi. It also equals phi times 1 over phi, or 1 over phi plus 1 over phi squared, or phi squared minus phi. Number 2 equals phi plus 1 over phi squared, or phi squared minus 1 over phi, or phi cubed minus phi plus 1 over phi. 3 also, so phi squared plus 1 over phi squared, or phi cubed minus 1 over phi, 1 over phi minus 1 over phi squared, and a few other, so it could go on, but so also 4, so we'll directly connect to that, but still phi squared plus phi minus 1 over phi squared, or phi cubed minus 1 over phi minus 1 over phi squared. So it's sort of, phi is hiding underneath all these numbers. It's built in to nature, it's built into, you know, basic geometry and so many other cool and beautiful things about that. So it's also like, you know, it's a beautiful number in that way. Now, I've done plenty of videos on how to draw the Fibonacci spiral, and I'll insert them in the links for some of them, so without drawing the Fibonacci spiral and going through all of that. And there's another way to consider it, and that's using the, so we have the phi spiral, but we also have the phi wave and like that, so best off to have a look. But so anyway, so we start with the Fibonacci numbers: 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55. Now, so if you divide these, so 1 divided by 1 equals 1, 2 divided by 1 equals 2, 3 divided by 2 equals 1.5, 5 divided by 3 is 1.66666, 8 divided by 5 equals 1.6, 13 divided by 8 equals 1.625, 21 divided by 13 is 1.615, same thing if we continue down, and the further we go down, the closer and closer we get to phi. So we'll go 1.617977. So now I have this, we're now going to make a graph, firstly beginning with the Fibonacci, and with this one we divided the larger number by the previous number, so the larger by the smaller. Now if we were to do that in reverse and divide the smaller by the larger, so we start with 1. 1 divided by 2 equals 0.5, 2 divided by 3, I have to get my, check out my, anyway, we'll start with these ones first, and I might as well do it. So, that doesn't work for me now. Okay, so 2 divided by 3 equals 0.66666. 5 divided by 3, 3 divided by 5, 0.6, and you'll just, anyway, you'll see it's just basically works out to be this minus 1. So the next one will be 0.265, so 8 divided by 5, and then 13 divided by 8, 8 divided by 13 I mean, would be 0.61538 dot, 13 divided by 21, 0.61904, and you'll see, so it's just this one minus 1, so it works again just like phi squared equals phi plus 1, or see this beautiful, so all phi minus 1 equals 1 over phi. This plus 1 minus 1 is a beautiful relationship there, and that's the same thing that's happening here using the Fibonacci numbers. Now let's plot out 1, 2, 5, and so we begin with the first one. So 1 next one is 2. Then we have 1.5. This fire line actually shouldn't be there, it should be roughly there. So this black line should represent 1.618 or phi. So 1, then 2, then 1.5, 1.666, then 1.6, and 1.615, and it's going to get closer and closer to this number of 1.618. So if we creates this, so this is the phi wave that we've graphed it out. But what's really nice about that, so for instance, what's the difference between 1 and phi? So how far is the first number? So 1, what's the distance from there to phi? Well, it turns out to be 0.618033 ... which is phi minus 1. But also, or 1 divided by phi. The difference from 2, so the second point, how far is that? Well, it turns out to be 0. Number right, 319. Now we'll get a few extra, so it's 660001, and well, what's that number? That number is phi equals 1 over phi squared. And so the margins of, so if you follow this through, the margins of error from these Fibonacci numbers, so that, yeah, the margin of error is actually a representation of phi itself. So one of the criticisms sometimes you might see is, well, the wave never actually reaches phi, or that it starts off far away from the golden number. Yes, but the margin of error is actually a representation of phi itself, which is why it is such a beautiful number, why it's in nature, in sunflowers, pineapples, artichokes, all sorts of beautiful things. So these, and again, from the vesica, it's one way to create it, one way to find out the exact number, also to do it as a ratio, and ultimately even the phi wave itself. So here is one side of the fib. Now if you were to do the same from here, you would also get, so let's do these numbers, so 0.5, 0.66, 0.6, and so if you, well, what happens is that you basically have the same thing happens, so it's just basically mirroring itself. So we begin with 1, and then we have 0.5. Again, I've drawn this phi a little bit too low, it would be somewhere around there. And so we begin with 1, then we have about 0.15, 0.66, and then you have the same thing. You'll get this same phi wave pattern. This is basically a mirror of this, and that's some of the reasons why the golden number, the golden ratio, the golden proportion is so beautiful, and why it's also in all these architectural the buildings I mentioned, sometimes very blatant, sometimes very subtle, but they all themselves, for instance, the Great Pyramid, the Louvre Pyramid by I.M. Pei, many other places, many other very important temple, grand public buildings, naology, the study of sacred edifice, and sacred architecture, and that's why phi is such a beautiful number. Cheers.
Yeah, this is going to be a video about phi and spreadsheets and numbers, and if you're not into that thing you might as well give up now, but in a few easy steps I'll show you how to create Fibonacci numbers, Lucas numbers, and as well as random numbers to look at what makes phi so special and how it sort of seems to underlie so many things in nature and physics. But without getting in, there's plenty of videos on that, you know, a lot of ideas, but just to begin with, we'll pick any square now. It's probably not going to say, if you've never used Excel or a spreadsheet, I've just opened a brand new blank generic ordinary spreadsheet. I haven't done any, so it's just open a new file in your spreadsheet program, and in this particular one you look down the bottom and there's a slider, and click across. I'm just going to zoom in so that each cell comes in clearer. Now, it doesn't really matter where you start, but just to make it simple, I'm going to begin over here on E1. I've left some over to the left-hand side, we'll get to that later. So but just to begin with, it's really easy to use these spreadsheets, and some cool things you can find out if you're into phi and your numbers. Now, first cell, E1, type in 1, enter, return. Next cell underneath, we type in 1. And we have the beginning of the Fibonacci. Now, from this we're going to create a simple equation and zoom in and zoom down as far as you want and expand the Fibonacci sequence as far as you want and see how important phi is. Now, so we have 1, 1, we've typed them in, cell beneath to open, create any new equation in, at least in Excel, we type equals. And then after that, all we have to do is click the cell above, E2, and we plus E1. Okay, now we've created a Fibonacci sequence. Now, so from here, all we have to do is click the 2, and here you'll see like a little dark box in the corner. So we find that, there we go, and we just drag it down. And we scroll back up to the top, and here we see we've created a Fibonacci sequence. And if I zoom out, you can see with the Excel, all those little numbers we can get to later, but it's as simple as that to create a Fibonacci sequence as long as you want to go. But that's not the point of this, so I'll scroll all the way back up to the top. And so here we have a Fibonacci 1, 1, 2, 3, 5, 8, 13, 21, on to infinity. Now, how do we find pi from that? Sorry, not pi, phi. To begin with, here on the screen, on the could be any side, it doesn't matter, just either side of that. I'm going to type in equals, click E2, or the divided by the one above it, E1, return. Now, just like that, I've created this box, and you'll see again there'll be a little black box right in the corner. We find that, and we drag it down. And there we have phi. Now, to expand in each of these columns, all you've got to do is find the edge, drag it across, and we scroll back all the way up. Here we see our Fibonacci numbers, very simple, click, 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 and then we see how we find phi. The ratio eventually will always return to 1.618033988, etc., etc., etc. I've got this set to just so many decimal points, but it's as simple as that. And now I'll scroll back all the way to the top, and here on the other side I'll expand the column out so I have a bit more room, and I'm going to do the exact opposite of what I did here. So click on that cell, equals E1 divided by E2. all you got to do is click on the cell that you're looking for, and it will do it automatically. So here on the left hand side, we've divided the number above by the number below, while on the right hand side we've divided the number below by the number above. And click return. Now, same thing, look for the little black dot box in the corner. We're just going to drag that down. Here we have the magic happening, 0.61803398, etc, etc. We're having these two ratios appearing. And now it goes obviously a lot more deeper than that. I just want to show you a quick, simple way how you can use Excel and find it for yourself. Check it out yourself. There are some really cool things if you, have looked into your business with Fire before.